The most common mistake on Mohr's circle problem is the very last step, finding absolute maximum shear stress. So we've got two different problems that they look basically the same, just with different numbers. We're going to solve them simultaneously, and we're going to show you how at the very end, if you mess up that last step, one of these problems you'll get wrong, and the other one you'll get correct just by dumb luck. And first step is always going to be to take your normal stress in X, normal stress in Y from your stress element and plot those on the X-axis for your diagram. So 10 and 20 on the left drawing, negative 2.5 and positive 5 on the right drawing. Halfway in between those is C. That will be the center of Mohr's circle. Now we're also going to plot a point on Mohr's circle. I'll call these A and B. And this is going to be at the X coordinate at sigma X, and the Y coordinate will be at the shear stress value. So for problem A, 20, 8, and for problem B, 5, -4. For shear stress, the right-hand side where I wrote the 8 KSI, if that arrow is pointing upwards, it's positive shear. If it's pointing downwards, like the 4 KSI, then it is negative shear. But then when you go to plot it on Mohr's circle, remember that the axis for shear is upside down. Positive shear stress is downwards on the plot. So positive 8 is below the x-axis, negative 4 above the x-axis. And this will come into play for other problems where you care about actually rotating to find like where the maximum stress is at the end. We're not going to do that for this problem, but there are other problems where this positive or negative actually does matter. All right, so starting to do some math, we can find C is just the average of our X and Y normal stresses. So the average of 10 and 20 is 15. The average of negative 2.5 and 5 is 1.25. Next, we can find the radius of Mohr's circle. This is going to be done via a Pythagorean theorem. We can just draw a triangle from the center to the sigma X and then down to point A. So this is going to be 5 and 8. Gives us a radius of 9.4. And on the other problem, again, from the center out to 5. So we've got the base of this triangle is 3.75, height of 4, gives us a radius 5.48. When you actually draw then Mohr's circle, the point on the very left is going to be kind of sigma 2, and the point on the very right, the positive most, sigma 1. These are your principal stresses. And you find the values for principal stresses as the center of the circle plus the radius to sigma 1 minus the radius over to sigma 2. So by adding and subtracting, so doing C plus R, C minus R for both problems, we now have 4 answers, which is actually getting us pretty close to the end of the problem here. So finding principal stresses on Mohr's circle is nothing to be scared of. This is just an average and a Pythagorean theorem. But finding absolute maximum shear stress, you have to keep in the back of your mind that this is not actually a two-dimensional problem. These stress elements are actually part of three-dimensional differential elements, and there's a third principal stress. Since we don't have any information about that axis, this third principal stress is just going to be 0. There's no forces in that direction. And with a third principal stress, and if Mohr's circle connects our principal stresses to each other, we actually have 2 more Mohr's circles we can draw, from sigma 1 to 0 and from sigma 2 to 0. So 3 principal stresses, connect them each to each other, you get 3 Mohr's circles. The maximum in-plane shear stress is just the radius of our original circle because it's straight up or straight down from the center. But the absolute maximum shear stress is the highest point of all 3 of these circles. So if the circle you started with was the biggest one, then the in-plane shear stress max and absolute shear stress max will be the same. But if your original circle was not the largest one, you'll get two different values. The in plane will be the smaller circle you started with. The absolute maximum will be one of the bigger circles that you draw later. So you have to be very careful when Mohr's circle is entirely on one side of the vertical axis, right? If it crosses the axis, then you know both other circles will fit inside it. But if your circle is entirely on one side, that means there's a bigger circle you can draw to connect it back to zero. That's when you're at risk of making this mistake. If you don't do this extra last step, you'll miss the absolute max shear stress. So in this case, problem A, on the left, absolute maximum shear stress is the radius of this biggest circle. So we just find the average of sigma 1 and 0, right, which is going to be 12.2 KSI. So that is the radius of the big red circle. That is how high the absolute maximum stress is above the horizontal line. And for problem B, on the right, the absolute maximum shear stress is the same as the in-plane max shear stress. It's the radius that we already found. It's the 5.48. The math is not hard, but if you haven't seen an example problem like this before, you do run the risk of making kind of an easy mistake because in-plane max and absolute max kind of sound like the same thing. It takes that little bit of extra understanding to recognize the difference between those, which is based on thinking of the 2D problem statement you were given as actually a three-dimensional stress element with 0 on the other side. All right. Great job, Serenity. You're doing awesome. Yeah, great job.